Hello, everybody, and welcome back to AI Images. Today's class is about diffusion. We're finally up to sort of the most cutting edge technologies. And so today we're going to walk through and look at how exactly diffusion works, including how it understands what words you're asking it for, and how it makes these images in the first place. So we'll walk through that, and we're also going to talk a little bit about what it means to make things. When we look at diffusion models, a lot of the things that we see from the interfaces that we use, the products that we're using to access these models, use words like imagine or dream. And I want to pick apart at that a little bit and think about what exactly do we mean by intelligence when we talk about artificial intelligence. So we're going to go through some sort of famous thought experiments about figuring out what exactly is intelligent about an AI system and where that intelligence lies. And then finally, we'll talk a little bit about the names of technologies, the history of technology, and where AI art fits. Is AI art its own thing? Or does it extend the line of generative art that goes back to, at least with computers, the early 1960s. We'll talk a little bit about that history, maybe compare and contrast some of that early generative art to the stuff that we can do today. And we're also going to talk about the critical response that came about to computer technology and art back in its heyday or origin point. Not all of which is going to sound unfamiliar to the critiques levied against it today. And that goes two ways, both that some of the stuff that we're doing might be sort of outside of any acknowledgement of the history of AI art. And it's important to understand where generative art lies and comes into play when we're making this type of stuff today. But it also holds true that critics have been saying the same stuff for quite a long time too. So we're going to unpack some of the criticisms around this technology. So without further ado, let's get started. And let's start thinking about part one, diffusion models, flowers blooming backward into noise. So I want to start this class on diffusion models at the beginning. Not just the beginning of diffusion models, but at the beginning of actual time. I'm talking about the Big Bang. For physicists, the Big Bang is this theory that one extremely dense point in the universe popped open. The universe expanded from that single point, and the evidence is the static on our TV sets. Buried between the images of television broadcasts is the microwave radiation that was unleashed by the Big Bang. We hear it on the radio, and it's rendered on TV as static and noise, breaking down all of our signals. What if you had to take all of those points of static swirling around on your TV screen and reassemble them back into a single image? How would you go about piecing together all that flying radiation back into whatever dense mass there was at the start of the universe? It sounds impossible, and it is, but how would you start? Jump ahead 14 billion years, and diffusion models start at the same place, a frame of static. Every image produced by diffusion models like DALL-E 2 or Stable Diffusion or MidJourney starts with this: a random JPEG of Gaussian noise, static. When we ask the diffusion model to create an image, the first thing it does is create a frame of random noise. It's going to take that noise and try to reduce it until it arrives at a picture. It's doing this similar to the ways we might look up at the universe out there in the nighttime sky, finding constellations in the random noise of stars. We see the Big Dipper, because that's what we've learned to see. But as we know, machines need to be told exactly what to find and how to find it, and these artificial intelligence tools really are no different. So of course, the machine isn't simply asked to go find a picture of flowers in the static. You have to train it. You have to make sure it knows what to look for. So how do you do that? How do you train a machine to find images in noise? Well, one way to do that is to start with some real images. So let's pretend this is an image of flowers we want to use in the training data. Diffusion models are trained by watching images decay, digital images decaying. They start with an image, and then they add noise. Gaussian noise follows a sort of rule as they break down, clustering around parts of the image. So let's add some noise here. As we do, you'll see the image is still pretty clear, even though it gets a bit noisier. What the model would do is sample these small differences between the two layers of noise. The one we saw before and the one we see now. And it would calculate the change based on one image compared to the next, as if it was a trail of breadcrumbs that lead back to the previous image. It will measure what changed between the clear image and the slightly noisier image. And then it does that again. And then it does it again and again. And it keeps doing this. And it compares and checks against the previous frame, but also against other frames in the sequence. And these changes will be taken into the model as an algorithm. So here we see the image has been nudged a little ways, and we're kind of on the threshold of losing sight of what this image is. The stems of the flowers are starting to get lost. We still see some key color variations in the petals. But here's what's important. This image, in a few more generations, is going to disappear completely. But the model will have learned the patterns found in the noise and the way the noise emerged along the way. And when it arrives at a frame of absolute static, it's going to have an idea of how to work its way back to the starting point. So towards the end of the cycle, the amount of noise can be introduced at a faster rate. At this point, you still see the very bare abstraction of these flowers, but you can still see them because the breakdown of this image is following a pattern where the density of certain pixels in the original image is still quite strong. Gaussian noise tends to follow a pattern. It's a loose pattern, but it's one that tends to sort of hang out around a central cluster of information in the image. In this case, that cluster of information is the flower petals. So this is something the machine is quote-unquote learning, or in realistic terms, it's accounting for this distribution of noise and calculating a way to reverse that noise. So, okay, we keep going, and at this point, the image is obliterated. The machine has learned how that noise spread across the image. Now, key thing, this is just one image that we're looking at. And it started from one specific complete picture, the source image. That source image was broken down slowly, and that breakdown was measured and remembered by the model. Now, if the model encounters a frame of static or a random image with static, it could apply these rules in reverse. In other words, it could attempt to reverse the breakdown of the image, that breakdown of the image into noise, and pull an image out of noise. And it would do this by following this path that it learned by tracing its way through the degradation of the image that we just walked through. But it's doing this with millions of images, with each image breaking down in its own way. Another way to think of this is its namesake. Diffusion models are named after diffusion, the same thing that happens when a droplet of liquid enters into a larger pool of liquid. It diffuses. And while the shape of the initial droplet is unrecognizable, you could still have a sense of which direction it came from. And knowing certain rules, you might even be able to trace that paint splatter backward Maybe not following the exact same trajectory, but at least you could get a rough sense of where the paint came from in the first place. And we're just talking about ourselves here as human beings. So instead of tracing paint droplets backward, the machine is working through new patterns of noise. It's predicted a pathway back to an image, but that image doesn't exist. So it's basically connecting dots in this noisy static, drawing something familiar from the training data. But what it's arriving at is a kind of abstraction of what's in the data set. Consider all the variables in effect here. You have an image with millions of pixels that is arranged as random noise. The model knows that noise breaks down according to specific patterns, so it begins to identify the most likely pathway back to some core image. The only thing is, we've tricked it. There is no core image. Let's think again about the nighttime sky. I can ask you to look up and find images amongst the stars, and you may find all kinds of different ways to connect these stars in ways that tell stories or create images. Maybe you'll find the state borders of New Jersey, like I did. But if I tell you to look up at the nighttime sky and find a constellation like the Big Dipper, you'll look for specific arrangements of stars that match your internal model of that constellation. And you might find it, even if it isn't actually there, as in this image where the Big Dipper does not actually exist. But if we're told to look for it, we might try to find it in the information that is available to us, which is basically the noise of stars in the nighttime sky. So how do we tell a machine to find pictures of flowers in the static? How do we tell it that? How do we say, I want a picture of a flower to a machine? How could a diffusion model find the Big Dipper in a nighttime sky that never contains the same set of stars? Well, much like we do when we're looking at the sky for specific constellations, when prompted, we can prompt the model with text. These prompts are going to constrain the possible paths that the model is allowed to take as it walks backward from noise. When we prompt flowers, for example, the model is constrained. It can't use what it's learned about the breakdown of cat photographs. But it has learned a lot about the paths that noise takes through the breakdown of flower images. So we could constrain it even further. Flowers in the nighttime sky, for example. Then you have a new set of constraints. Flowers, but also night, and also sky. You can set style constraints. Here we have an image taken on a specific type of film, for example, giving it a specific sense of time. Your prompt becomes part of the information available to the model to make sense of the image that it's being asked to make. The prompt becomes part of the information available to the model to figure out how to turn noise into that image. It starts with randomly generated noise, but we say, actually, this isn't noise, it's a picture of flowers at night. And then the model works to uncover the noise from the photo towards this image that doesn't actually exist. Take it step by step. You type a prompt into the model. The model understands your prompt as a set of words. These words are actually combinations of letters. They may or may not be words. And these are like triggers that are associated with specific mathematical recipes for rebuilding an image that has been lost to noise. The model then applies this denoising to a randomly generated JPEG of nothing but noise, pure noise. And then it works that noise in reverse, attempting to predict its way back to the source image, but the source image doesn't exist. At every step, it's reassessing what it just did and how what it just did compares to the patterns it has learned. And it's sharpening this picture. It's creating outlines loose ideas and conceptions of the image. And then when it has a sort of almost like coloring book version of that image, it's using that as a guide to figure out where to remove even more noise and how to shape and steer its way back to the original image. But as it keeps denoising, that image becomes a little bit more clearer, and so the model has sort of more information to work with. So finally, you end up with an image that the machine has never seen before, not in the training data, though sometimes they do leak. We'll talk about that in a minute. But this image is based on millions of images that it has learned to break down, that it has seen before, but it is an image that more than likely does not exist anywhere else out in the world. And in the end, it takes the output of this process, it strips away what we've asked it to do, and it actually compares what we've asked it to do with the same picture as if we didn't ask it to do it. And it compares that, and it uses those two pieces of information to sharpen it even further, to refine the image with the text information in it even more. So basically, there's this final step of comparison that is used to polish up the final product. So that's the heart of diffusion models. But there's another key piece, which is how do these diffusion models know what your prompt even means? There's a few answers to that question, but both come down to new ways of categorizing training data. You may remember from our talk on generative adversarial networks, or GANs, that GANs are limited in that you had to train a single category of data at a time, and it was often unreliable. If you wanted to create an image of a cat, you had to generate a cat from the cat dataset. And if those data sets were hard to build, then they were less likely to be complete. They were less likely to be good data sets and less likely to generate good images. As OpenAI writes, the ImageNet dataset, one of the largest efforts in this space, required over 25,000 workers to annotate 14 million images for 22,000 object categories. In contrast, CLIP learns from text-image pairs that are already publicly available on the internet. So CLIP is the system that is doing the work of sort of linking all of these, what we used to use individual data sets for, literally kind of folders with images of the same thing in them. CLIP is a way of, instead of looking at specific images and being told these images are cat, CLIP is a way of looking at the text and the image associated with that text in captions online. Now, they mentioned that 25,000 workers created that first ImageNet dataset that was used for GANs, but I will point out that you and I built this system. Whenever we put a picture online with a label describing it, we are doing the work. So we moved from 25,000 workers to billions of workers. Any internet user who has ever labeled an image online is part of this, potentially part of this data set. So, point is, the idea is that the information in an image with the label picture of a peach was probably going to be a peach. And if it wasn't, it would work itself out. There would just be so many pictures of peaches with the label peach that the vast majority of these photos with that label would be peaches. The text that these models draw from includes not just captions, but also alt text, the text behind images that are designed to be read aloud by text-to-speech systems for web users who use assistive technologies. So CLIP stands for Contrastive Language Image Pre-training. And it's an image recognition neural net that doesn't require categories in advance. It works its way through labeled photographs on the web. And it's been designed in a way that assumes a connection between the pixel information in the image and the text used to describe that image. CLIP is a way of navigating that information, and it was applied to something called the Common Crawl dataset of internet images. Now, OpenAI's data is proprietary, it's not public, so we don't really know what CLIP did for their dataset. We don't know what that dataset looks like. But a similar open model, LAION 5B, contains about 5 billion text-image pairs in a similar framework. But in this case, we can go look at it. Stable Diffusion is built on LAION, and so is MidJourney, though each of these tweaks the data to encourage specific results based on the sort of aesthetic choices that they want to encourage in their output. So if you notice that Stable Diffusion looks a little different than MidJourney, that's part of why. They've tweaked what they're using from LAION. What's common across these tools is that typing a prompt constrains the model into a narrower set of options for what it can make from the noise. It goes from looking at any image at all in the noise to specific images based on your guidance. Those options are learned from the labels created by humans, like you and me, who upload photographs to the internet. Now, the problem with this approach is that the internet is written by people, and people are not always kind, and people are not always accurate. And LAION has a lot of problematic representations in the dataset, including stereotyping, violence, and pornographic imagery. Even when these images are censored from the final output or input, they nonetheless shape the collective understanding that the model has made of the images in that dataset. In other words, you might have a violent image in your dataset, and you may say, I'm going to take this out. But the model, if it has seen it and learned, kind of already is associating that with other things that may be unanticipated. Here's a random screen grab of LAION's training images for the word American. And you'll see plenty of stereotypes at work, from big gulps to flags to guns to a man tackling a deer at a Walmart. And these kinds of stereotypes are pervasive because LAION is categorizing all of these images according to the internet's description of them. It's not really that there are stereotypes in the dataset, which is certainly true. It's also that the dataset is literally built on describing commonly associated things into the same label. In other words, the existence of LAION and the way it works is through stereotyping. So this can create problems. Not everything is going to be a problem in this. You can stereotype an apple and come up with a pretty accurate image of an apple. But when you start getting into people and social categories and more complex questions, you come to new questions about what's included and why, and how that's modulated, moderated, and what decisions go behind shaping the way they come out, the content moderation of the output. So in later classes, we're going to go into what the internet has to say about people and the things that shape the output of these systems in often problematic ways. Before I move on, I just want to talk about a kind of crucial question around diffusion right now, which is, can the training data, without any alteration, ever be generated to a user? In other words, if you put in a prompt, is it possible to get an image from the data, the training data, that is more or less not abstracted into something different? And up until about 2 weeks ago, this was an open question. People didn't know. But thanks to this paper from Carlini and others, called Extracting Training Data from Diffusion Models, they actually went and found out that, yes, you can. It's unlikely. And in fact, they generated 175 million images, regenerated training data 109 times out of 175 million images. But the possibility of data leakage matters. This is from a security privacy standpoint. If this image sort of you're gobbling up all this data online, how do you know that if it can generate a image of Anne Graham Lotz who is an author, that is more or less exactly the same as an image that she's uploaded to her website, how do you know that your face will not appear on someone's image that they're generating? And how do you, especially if you haven't given permission for your images to be used, which is a huge controversy that we will address in this class. But if your image is on the internet and your image has been labeled with something, perhaps even something unflattering or mean or bullying, perhaps you are, or a hypothetical person is the victim of online harassment, and someone types in a negative phrase and suddenly the victim's face appears in a otherwise abstracted image, that's a real problem. And the user who sees that face may not even know that it belongs to a real person. Think of how many images we see that are not real people. How do we know? And this is an important question that has emerged really recently in the conversation around diffusion models and online safety and security protocols around the training data and whether or not it can leak. And this is called data leakage from the training model. So this is something I wanted to mention. It's a relatively new discovery. But for now, I want to go back to thinking about what the model does and how we make sense of what it's doing. The story we tell ourselves about what artificial intelligence is. So now that we know how diffusion works on a technical level, we should note the words that are often used to describe this process. Is a diffusion model imagining a photo? Is it dreaming of a photograph? The technology is incredible, there's no doubt about that, but is it anything akin to the workings of a creative human unconscious? Not even as a value judgment, but as a comparison. How accurate is that comparison? Well, it turns out this is a classic debate in artificial intelligence that predates artificial intelligence and images.
Never before has a computer attempted anything so profound. We seem to be witnessing the spawning of a new kind of intelligence, artificial intelligence. Already, many computers are behaving like infant prodigies. What will they do when they grow up? Faced with such a rapid rate of evolution, it would be reckless for us to make any predictions.
This debate centers around the name itself. Can the tool understand what it's doing? Is an artificial intelligence system actually intelligent? Some would argue that the way diffusion models make art is identical to how humans make art, and therefore the AI can be identified as the artist. Others challenge that concept, saying there's a key distinction between human minds and computers. This debate, more or less, is a repackaged debate around the Turing test, otherwise known as the imitation game. This is the idea proposed by Alan Turing in a 1950 paper that if a machine could write text that could pass as human, it should be considered intelligent. A challenge to this proposal came in 1980 from philosopher John Searles in a paper called Minds, Brains, and Programs. Searles suggested a thought experiment. He imagined himself locked in a room with boxes of papers, and on those papers are Chinese characters that Searles can't read. There's also a book, and the book is like a dictionary, but he can go and look at the Chinese symbol, but he can only find, instead of a definition in a language he can understand, he can find out which box he's supposed to go to in order to pull out another Chinese character that he doesn't understand in order to hand it over as a response. So you're in a room, there's boxes of Chinese characters on pieces of paper, and there's a book, but the book isn't a dictionary that explains what the character means. Instead, the book tells you where to go to pull out another character if you see another character. So you're in this room and a note slides under the door. It's the letter from a native Chinese speaker. Searle, who imagines himself in this room, takes the note, goes to the book, matches the symbol on the note that he got to a symbol in the book, finds that the book is telling him to go pull out a response from, say, box 11. So Searle goes to box 11, grabs a piece of paper from that box, and slides it back under the door. The Chinese speaker on the other side is satisfied. This was a proper call and response interaction, as far as they're concerned. But the question that Searle poses is, does this mean he understands Chinese? This is a thought experiment, and there are many responses to this, as there often are in philosophical discussions. One of them is the clear answer that Searle gets to. He says no. He does not speak or understand Chinese any better at the beginning of that experience than he did at the end. There are other arguments, however, which suggest that, well, maybe Searle doesn't understand Chinese, but maybe the room understands Chinese. That is to say, one might look to the room as a system, the way we look at a translation engine, and say it understands Chinese. Searle's counter-argument to that is that the room doesn't actually understand Chinese. It just realistically simulates the understanding of Chinese. The room cannot understand the meaning of the words that it is producing. But if you look closely, it's really just a manipulation of symbols that takes place inside the room, with him as the actor, here substituting as the quote-unquote artificial intelligence, going and finding which symbol matches what, and serving it up as a response. So he would still say the room, as a system, still doesn't understand Chinese. Now, if we extend the definition of this system to the person making the request, we might say that this person is having an interaction. If the person outside the room can have a conversation with the system inside the room, then together they form a kind of understanding of Chinese. But this is very different than saying the room itself understands Chinese. So this is an AI art class, so I want to reframe this Chinese room experiment a little bit, and I want to call this version of the thought experiment the puzzle library. And to make sense of this, I want to consider the art of Tim Klein. Tim Klein is an artist, and he realized one day that the jigsaw puzzles he'd been looking at were all using templates. In other words, if you bought a particular brand of these puzzles in the 1980s, they all had images printed on the same set of puzzle pieces, meaning they were interchangeable. You could take a piece from a leopard puzzle and you could plug it into the exact same position as a castle puzzle. And Klein realized he could draw from these pieces and assemble them to create new images by combining pieces from different box sets. This is a good way to think about diffusion. It is able to assemble many different categories together into the same image, which is a huge leap over the stricter categorization of GANs. So now, instead of being locked into a room with boxes of Chinese characters, let's say that we're locked in a room with a bunch of these puzzle boxes. And these puzzle boxes, each of these pieces is taken from various puzzle boxes based on where they occur in the puzzle. These puzzles are fragments scrambled up, and we don't know what the image they make actually is. It's just pieces scrambled up. And instead of looking at them as pictures, we're looking at them as their position in the puzzle. Each of these boxes and pieces is numbered, and there's a book that tells us which box to go to and which piece to pull out. Just like the Chinese room experiment, a note slides on the door, and it's an artist outside the room with a prompt. You bring the prompt to the book, you look up each word in that prompt, and you write down the corresponding number that the book gives you for the box and the piece. And then you go to that box, dig around for the right piece, and you put it onto the board as you pull it out, in the sequence instructed by the book. In the end, the man in the room has assembled an image. But does the man in the room understand the meaning of the image they made if they haven't looked at the pictures and only looked at the numbers? Do they understand the meaning of the boxes these pieces came from? In this thought experiment, the person outside the door is the prompt writer, and the person in the room is moving information from Clip and LAION, which has assembled text and image relationships into sets of probabilities. From these probabilities come instructions for where to go find pieces of an image that are being requested by the prompt. And the question Searle might ask is, did the person in the room, the AI, make this art? And I would suspect he would say no, because the person did not act with the intent of making art. The person acted with the intent of finding pieces together from a set of rules. Earlier in this course, we heard from Paul Pangaro and the cybernetic view, which Searle doesn't address. But the cybernetic view might ask, did the person outside of the room make something? And the response from that view might be, if the person outside of the room could have a conversation with the person inside the room, then together they might form a kind of art making. But in Searle's experiments, and in the way our current technologies are shaped, that's just not possible. It's a black box. The room does not allow you to enter in and shape which pieces of the model the actual output is going to pull from. You could constrain it. You could say, I want it to be a lion, but you can't really say which lion or what the lion should look like. You can't say which type of flower you're going to get if the abstraction only knows flower in a kind of abstract sense. The puzzle room metaphor may not be the best parallel, but the Chinese room debate is an interesting and important one in AI circles. Searles would say that the person inside the room is simply moving symbols from one box to the next at the instructions of a book in correspondence to the requests of the person outside. If the person inside the room can't be said to understand Chinese, then I would suggest we shouldn't give it credit for making art either. Another response to this paper came from Cole in 1991, suggesting that if there's any understanding of Chinese emerging from the room, that understanding is from the one who wrote the instructional book that Searle is following, the person who put together the boxes of Chinese characters. This reflects the position that in these closed-off systems, what matters is the data and the program. The data and the program don't understand. They enact rules created by someone who does understand. Thus, Cole writes, we could consider the room a kind of virtual mind, or a virtual extension of the person who writes the code. Another argument comes from those who defend neural networks as metaphors for the human brain. Because humans can understand, and because the neural networks are modeled on human brains, the argument is that the process of translating Chinese through a neural network is much closer to human understanding than Searle is giving it credit for. Searle addresses this too. He proposed that the human in the room was now activating a series of pipes. So think about the room changing shape now. Instead of just a room with a box and a book, you actually have a series of pipes that are laid out that map an exact replica of a human brain, the way that these complex neural networks claim to rival the potential circuitry of the human mind. No one's claiming we've done that yet, but this is the theory that is intended to be aimed for in the neural network view. So the man in the room is given instructions for how much water flows through pipes that are arranged to flow electricity in an exact replica of the way that a human mind has neurons shifting chemicals and electric activity. So the water then ultimately pools at a level that indicates the location of the proper Chinese character, or in our case, the box with the puzzle piece in it. Searle puts it this way. The man still certainly doesn't understand Chinese, and neither do the water pipes. And if we are tempted to adopt what I think is the absurd view that somehow the conjunction of man and water pipes understands, remember that in principle, the man can internalize the formal structure of the water pipes and do all the neuron firings in his imagination. The problem with the brain simulator is that it is simulating the wrong things about the brain. As long as it simulates only the formal structure of the sequence of neurons firing at the synapses, it won't have simulated what matters about the brain, which is namely its causal properties, that is, its ability to produce intentional states. So what Searle is kind of getting at here is that it's not really about mapping the structure or the arrangement of the human mind. What matters is replicating the potential for intention to activate that model, to activate that flow. So this is a key question to ask about artificial intelligence. Where is intention located? Where is agency to change that intention? If an AI system is an extended virtual mind of the algorithms and code it follows and the data that it has been designed to collect, can the AI be said to have any agency? Can the AI have any freedom of choice or intention to put into the outputs that it makes? Or is it more accurate to say that the person outside of the system, the user, the designer, is the one who has varying degrees of freedom over that output? I leave this question to you, of whether AI understands or is able to produce its own meanings when it makes artwork, or if that meaning is made by the viewers and the designers of the system, the people using the system, the people like you and me who are looking on from the outside. This brings us to part 2. I want to change the conversation a bit to another question, which is how we describe the products of something like DALL-E 2 or Stable Diffusion. In the early days of technology, we often don't quite know how to name stuff. Today we have a debate around whether AI images should be called AI images at all. Some question this idea of artificial intelligence as a phrase. Some prefer image synthesis or generated images. In the early days of photography, you had similar discussions, and a quick look at the proposed names for the images that come out of cameras shows you how people were grappling to make sense of that technology. Many of these names focus on the capture of light, a key aspect of camera technology where light hit chemicals on film, and the film reacted in ways that captured the image. Before we called them photographs, we had different proposals: photogenes, heliographs, photograms, sunprints. None of these caught on, but they all tell us something about how people made sense of the new technology. Photogene, for example, is borrowed from this word for the after image burned into our retina just after closing our eyes. So if you close your eyes and you see this sort of reverse image of the bright things in the room around you, they wanted to name photographs after that phenomenon. So today we have a debate about whether AI images can be called photography, if there is such a thing as AI photography. Some, again, as I said, prefer image synthesis or generated images. And frankly, the images made by diffusion aren't photographs. They don't capture any light at all. So if we're going to be literal about the meaning of the word photograph, an AI image is not a photograph. An AI image produces light. They are purely digital images. They are producing information about which pixels on your screen should be lit up. So we can't call them photographs if we want to be true to that meaning of the word. So the question then would be, if these images don't capture light, what are they capturing? Well, as we've seen, I would argue they capture categories. They've looked at billions of images, they've sorted those images according to labels, and when we produce an image, we're doing it through a prompt that activates those categories and then inscribes those categories into the image that we're given. So just as light was so important to photography, I'm going to argue that data is equally important to AI-generated images. This class is going to spend a lot of time thinking about data and algorithms and how information gets assigned to these categories. They reflect decisions, structures, and assumptions about the world. Most fundamentally, the assumption that internet captions will appropriately describe the images that they contain, and that this can be used to create abstractions that serve us in a multitude of various contexts and uses. So we're going to look at the vast body of work that talks about algorithms and the human biases that algorithms contain which can be the result of deliberate and intentional choices as well as unintended ones. This relationship of data and categories to these images can be thought of as a distinct marker of the art form. But it also, I would say, AI images comes from a fairly long lineage of generative artworks. The data revolution has radically changed what these works look like. But the fundamental definition of generative art still holds true. Here's one from 2003. Generative art refers to any art practice where the artist uses a system, such as a set of natural language rules, a computer program, a machine, or other procedural invention, which is set into motion with some degree of autonomy, contributing to or resulting in a completed work of art. Now that quote comes from 2003, but it's said that the first generative artworks were possibly displayed in February of 1965 by Georg Nees and Max Benz. Nees was working at a technology company and had been writing rules for a computer to follow to draw images using simple algorithms. In the 1972 Computer Art Exhibition Catalog, an exhibition of computer art which took place in India, the process was described in a way that might sound familiar from the start of this lecture when we described the production of random noise and the rules the computer followed to turn it into an image. But this is describing early 1960s generative artworks. Through these programs, the computer receives a series of instructions, from which it then calculates the configuration of the finished work. This can either be displayed during the process of calculation on a screening device, or the data can be first fed onto a magnetic tape or onto a punch tape, by which the output devices are then controlled. A characteristic of many programs for aesthetic structures is the inclusion of chance. In the structural scheme, some parts remain empty so that they have to be dealt with during the process of realization. The program does not provide a single work of art, but a whole variety. For the determination of the independent variable is a so-called random generator. Here one can use a physical device, which provides random impulses, a Geiger counter, for example, which registers the irregular impact of radioactive particles, or a frenzy generator, by means of which disruptions from the atmosphere or from inside the machine are amplified by electronic conductors. So basically, what they're describing is a generative artwork where noise enters into the system, but it triggers a set of responses that follow a certain set of rules. So this is generative art being described in 1972. And it's being used to describe art that's existed since 1965. Here's another work by Mezei Leslie from that 1972 exhibition. This is called Transformation of a Girl's Face, contrasted with the output of MidJourney, asking for the simple prompt of a girl's face. Leslie's work starts with a computer drawing, and it transforms this drawing algorithmically according to the code. Arguably, that's what MidJourney is doing on the right. The difference between the two is not necessarily this underlying principle of generativity. The difference between the two is the vast size and complexity of the data set, which, as we've mentioned, is the internet, as well as the processing power we have on hand to automate the analysis of those data sets and to enact that analysis into the production of images. While the aim of artists who work with generative art varies, I just want to point out that generative art is not radically new, but that our capacity for detail has changed. The power that drives these systems is radically, exponentially larger. But debates around the definition and role of the artist in response to computation, to automation, they've been renewed, and we should have those debates, because fidelity and realism in computer-generated images certainly does change the game. It raises the specter of illustrators losing jobs, of digital artists being automated away to machines that can now generate children's books or game art. These are real concerns, but what I want to say is that they're not new concerns. A lot of questions have been raised around generative art, and we're hearing them again today around this new thing, quote-unquote new thing, we're calling AI art, but it follows a long tradition. Back in the 1970s, a New York Times art critic suggested that computer artists were too concerned with the use of computers to make art in forms that already existed. He writes that the artists in a computer exhibition rely too much on the imitation and conventions of recognized forms of art. Rather than using computers to create paintings or drawings that a human could already make, he wondered, why not emphasize things that only a computer could do? So let me just read this clip from the New York Times, 1970, from John Kennedy. Exhibitions of computer art have been popular sideshows for several years now, and about 40 examples have been assembled as part of the convention's program, which has its overall goal, quote, to interface the computer industry with the problems of society and the world, unquote. The least of these problems, it seems to me, is to teach computers how to give us more of what artists are already giving us too much of. If the computer is going to be used as an art tool, it should be used to produce art peculiar to its peculiar nature. Art which, like the pattern illustrated to the left, is literally impossible of execution by hand. Called the snail, the black and white drawing, 36 inches high, is one continuous line of uniform width that, if unwound and stretched out straight, would be about 8/10 of a mile long. This is my own old-fashioned, non-computerized figuring. The machine in question, a CalComp 702 plotter, draws at the rate of 3 inches per second, and the drawing took 4.5 hours of its time. I want to point out a few things. First of all, the description of the computer art exhibitions as a popular sideshow, right? Not exactly flattering. But also this weird position that there's just too much art already, which is an unusual position perhaps from an art critic. But contributing more images to an image-saturated space is an interesting idea, and we're going to touch on that in future classes. But I want to bring attention to the fact that the snail is uncredited. There's an illustration of it here, which appears with the article in the New York Times, in the 1970 edition of the New York Times. And the only credit given for it is the CalComp 702, which is a plotter, as it says here. So just pay attention to that, because this is where a lot of the discourse around computer art was back at the time. So this critique, this criticism, this resistance is nothing new. This dismissiveness is nothing new, even among art critics who saw enormous potential in the medium, and maybe especially within critics and artists who saw enormous potential in the medium. This kind of tacks on to this argument of why are we building AI to draw pictures when people can draw pictures? Why potentially put artists out of work when we need artists? We want artists. So we start unpacking this back in 1970s, these questions around, well, should a computer be making art that humans could make? Is there a possibility for a computer to do something radically new? Is there something that a computer could do that humans can't do that we should be focusing on? And I just want to point out that this conversation continues. It's not a new conversation. Another artist, Robert Mueller, writes in Idols of Computer Art in 1978 that he's tired of a set of cliches, which he calls idols, in computer-generated art. The cliches are these. There's idols of nature, which are landscapes, flowers, plants, and trees. This is boring, he says. Why use computers to represent the natural world? This has already been done by humans, drawing and painting and sculpting. So what can computers do that go beyond this? He suggests idols of the formula. Here he defines it as mathematical formulas that generate shapes, but maybe they're shapes that are so abstract that humans can't actually find a way into them. They're chaotic, they're hard to comprehend. They don't really tell stories or move the viewer. So idols of the formula, he suggests, are just sort of people using computers to create images from complex formulas and algorithms that maybe don't connect to art as it was traditionally defined. Why do that, he says. Another cliche is the idols of the kaleidoscope, in which this exact same mathematics are used to create symmetries that are too pleasing. In other words, symmetries that are too comforting and too easy to understand, but don't challenge the viewer in any real way. That's idols of the kaleidoscope. He has another list here, idols of the game. That is, works that make use of pure randomness without any tension with order or control. So, random noise generating engines, art that uses a computer to simply make random things. He suggests that this is actually not particularly interesting, and that it's the tension between randomness and order that creates interesting work. His other concern are the idols of disguise. Taking old works and making them quote-unquote new through the eye of the computer. That is to say that a computer could create a version of another famous artwork. Here in the slide, you see a reinterpretation of Paul Klee being done by a computer. And here Mueller says, why are we doing this? Why do we need to create a computer-generated Mona Lisa? Why put our attention into recreating existing artworks as if the computer is going to transform them? Why not put our attention onto the generation and production of something new? And this comes to mind with a lot of the conversation around things like we saw with Jodorowsky's Tron, or using the style of living artists or other artists in order to create works that are quote-unquote new versions of the artist's work. Or how might Wes Anderson imagine Star Wars, right? So when we ask these questions and we combine existing styles and existing artworks, what is that recombination suggesting? Why is that interesting? Mueller wants to ask. And I think that this is one that we hear a lot of in the current moment. And again, he's raising these in 1978. The last one is idols of the eye, the use of computers to generate optical illusions. His point is optical illusions in and of themselves are not saying very much. They're interesting, but they can quickly lose interest once a viewer sort of understands them. So creating art that sort of just quote-unquote looks cool, maybe that's not enough. Maybe that's not interesting enough. And Mueller here is suggesting that that is another barrier that computer artists should be working and thinking about transcending. It's a crutch. All of these are cliches or crutches that artists are relying on.
So I want to point out that this guy was calling out computer artists back in 1978, and he was an artist himself. So he was not necessarily just being a pessimist about everybody else who was making artwork, but offering this as a legitimate challenge to think through some of the cliches that he had seen and to try to transcend those cliches, both himself and publishing it, obviously encouraging other artists to try to transcend those cliches. And this was nearly 50 years ago. And a lot of these cliches are, of course, very familiar. They're things that we still see today. We see artists doing them today. And a good number of art critics and curators and writers who have a long understanding or an understanding of the longer history of generative images and artworks often echo these criticisms. If you think that AI art came about when DALL-E 2 came around or Diffusion came around, you might be tempted to see everything through the lens of this revolutionary technology. Everything's going to seem new. Everything's going to seem pretty radical and different. But if you look at the pieces that people are generating today through that long lens, that long distance lens of art history and computer art history in general, you might be a little harder to impress. Dare I say, you might even be a little jaded. The novelty just isn't there in the same way that it is for someone who's encountering these tools for the first time. As practitioners, it's crucial to find a balance between these two positions. Most of us aren't aiming to have our diffusion work reviewed by the New York Times or in a fancy gallery, or acquired by a museum. Right now, we're all trying to figure things out, and we're all curious, and we're engaged in what these technologies can do. And of course, there's a long history of art where students and newcomers to a medium imitate and refine the work of others who've come before. And so some amount of duplication is probably going to be expected as we get started. In this class, I want to encourage you to dig into some of the histories we're talking about and mine them for new ways to play with the tools that you have, setting aside any desire to make something radical or revolutionary. Odds are, something you're going to make has been done before. And at this stage, I think that's perfectly fine. The ambition, the goal as an artist is obviously to make something new and compelling and that no one has ever seen before. But I'd rather that you hold on to any excitement for the potential of these tools and use that as fuel to try out new things and be playful and experiment. Because the argument about what's new in art is also a little bit of a cliche. There's a long history there too, and I hope eventually we can have some conversations around the role that human artists are playing in these data sets that we're drawing from, and the complex question of appropriation. Are we simply taking other people's work and presenting it as something new, or are we actually combining things in ways that make them truly new? And what does new mean? And what does truly new mean? These are very open questions, and I don't think we're going to get to answer them in this class, but we'll do some thinking about them, hopefully later on. For now, I encourage you to lean into the excitement you have for these tools, if you have some excitement for these tools, and explore them with a sense of curiosity, but also just to think through, as you're using these tools, about ways to tell your stories and ways to make something that feels like your own. And on that note, I just want to say thanks, and I'll see you in our next class session. Thanks so much. Bye.